Rates of change and derivatives. So we're making a change ourselves. We're going from limits and so on to moving up to the big time with some rules and so on. So let's see what this is all about. On the upper left, I thought this is a nice picture. It shows going from this spot on the graph over to this spot. In the process, you go over a bit and up a bit. The ratio of those two is the slope between those 2 points. Notice that at this point, think of it in terms of walking up there, or bicycling if you like that. This would be a little bit steep. Over here, you're going downhill, that's a little bit easier. Over here, you're going uphill again. And you can see some of the numbers here that will give you a slope. Slope is the rise over the run. In fact, that's a carpentry term. What's a derivative? Okay, you can read that. And before we get rolling too far, I'm going to sneak in here with my pen and choose a little bit of red. So let's go. Alright, you've by now gotten a little bit familiar with average rate of change versus instantaneous rate of change. Average rate of change is usually a time period, and it's over a time period of maybe hours, minutes, seconds. It depends on the situation. The instantaneous is how fast that's happening at a particular instant, no time period. And that's very important. For the average rate of change, time period. So be very careful. Sometimes when you least expect it, let's blame this on the book. When you least expect it, it's going to ask for the average rate of change. Make sure you keep your eyes open for that, because it'll sneak up on you. And it insists on a time period. So that delta y over delta x you're familiar with from algebra, this part right here is not always a tiny thing. There's a time period involved. Like I said, seconds, minutes, hours, days even. Instantaneous means how fast you're going at one particular instant, as in instantaneous. So when you're driving, for example, and you look down at the speedometer, that tells you what your instantaneous rate of change is, or instantaneous speed, as opposed to the average, which is how fast you'd be averaging over 3 hours or 5 hours or 7 minutes or whatever the time period is. Remember, time period for average rate of change. We'll do a little bit about interpreting a graph, looking at the picture, see what we can find out from that. The instantaneous rate of change, here is the derivative. We have spent some time doing this with the difference quotient, which is this part on the right hand side, and that's only if the limit exists, of course. So here we go, average rate of change. Note that we're not trying to make this part as close to zero as we can. It's whatever it happens to be, from this point to this point. And remember, this y value is the one you use in the function using that x value. And this y value you get from putting this value into the function. There's your function. Remember, f is just a name for the function. You call it Fred if you like, Frederick, whatever you like. F is nice and short though. Here's an example, and you're trying to find the average rate of change. So instantly you think, okay, some time period. In fact, Another way of saying that is there's an interval from one x to another x. So on the bottom for that, you're going to use 6 minus 1. You can take the second x minus the first x. What do you put on the top? Well, those are the y values. Remember, delta y over delta x. But what are the y values? Y values, this is the function you're using right up here on the upper right. This tells you if you use that value for x, this is how you calculate the y value. So down here, f of 1, just put 1 in for this function. Put a 1 in here, a 1 in there, and find out what you got. In this case, if you put a 1 in, you get an 8 from that function. If you put a 6 in, you'll end up with negative 69 halves for this one. Not very elegant, but it's what we've got. So those two y values will go in here to get the average rate of change. Just put those in. You might want to use a calculator for that. This is sort of old school with those 2's and everything. The calculators are probably your best bet. Again, average rate of change. There we go. Change in the output divided by the change in the input. Just another way of looking at it. Remember, the x are what you start with. The f of x's are what you get from those x values. Short story, subtract the y's on the top, subtract the x on the bottom. Next, how about the function y equals 2x plus 1? What's the average rate of change? So, average. So we're going to go from 0 to 3. So, x of 1 is 0. X of 2 is 3, if you'd like to do that. We're also going to need f of 0 to match up with this. If I put a 0 in for this x right here, 2 times 0 is 0 plus 1, you get a 1. Remember, this means that you've got the ordered pair 0, 1. The second one, you're talking about an x of 3. So you put a 3 in where the x is. Go up here. 2 times 3 is 6, plus 1 is 7. And there's your second y coordinate. And this corresponds to 0.37. Now it says, what's the average rate of change? So you take this delta y over delta x, subtract the y values, the second one minus the first one, the x is on the bottom, the second one minus the first one, and we get 6 over 3, also known as 2. There's our average rate of change of y with respect to x. Because it all goes back to x, even though we're talking about the y's. It's how the ratio is. As long as it's a linear function, which this is, you can tell this is a line because it's in slope-intercept form, and also because you've got a first degree y and a first degree x, so you're going to get a line. There's a little bit of a summary, and there's a picture. Here are our points. That was the first point, this is the second point. Remember, we put the 0 in for f, got a 1, put a 3 in for x, into f, and got a 7. Next, how about this one? Average rate of change, and we're talking about f. F is 2 over x. So what does that look like? We want delta y over delta x. And we want to go from x to x plus h. And let's start with the easy part, the x's. This is your second x value, and this is your first x value. We're going to subtract those for the denominator because we want delta x, change in x. On the top, we're going to take f of x plus h minus f of x. That's the easy part. Now, on the bottom, notice the x's will give us 0. All that's left will be the h. That should look familiar by now. On the bottom, let's extend this fraction bar. We're going to be subtracting the original fraction, which is 2 over x. And what we're going to start with is 2 over. Remember that trick I told you? Just put a blank where the x was. And then, what should be there instead of the x? X plus h. And you're ready to roll. You might not like it, but this is what we've got. Now you need a common denominator. You've got denominators of x and x plus h in the numerator. Right there. So what you need is a common denominator, and it has to have x as a factor and an x plus h as a factor. So, fortunately I've got enough space here. I need this one to also have an x in the denominator, so you get this common denominator. To do that, you're going to multiply by x over x. So you're just multiplying by 1, everything's still good, but you'll have a common denominator. On the other one, you already have an x in the denominator. What you need is an x plus h as a factor. And of course, this has to be equal to 1. So there, this will give you the common denominator. What's that give you? Well, it looks like a mess at first, but let's see. So on the first one, notice you've got 2x over x times x plus h minus, and over here you'll have 2 times x plus h over x times x plus h. Remember, that's just the numerator. And down here, there's h. Okay? Take this up here, give us some room. What do we have now? Well, we've got a common denominator, so we can just add the numerators just as we would with ordinary common fractions, which these are just a little bit more sophisticated. So on the top, let's draw a fraction bar there. On the bottom will be h. On the top, you have a common denominator of x times x plus h. In the first part, when you add these two together, the first fraction is going to contribute a 2x. You're going to be subtracting what you get from the second one. Notice this is a minus 2 times x plus h, and that'll look something like this. Minus 2x, that's the minus 2 times the x, and minus 2 times h will give us minus 2h. Alright, we're getting a little bit closer. Now this h we can think of as h over 1. So, next, on the top, notice this and this give you 0. So on the top you've got minus 2h, and our common denominator was x and x plus h. On the bottom you had h over 1. Well, this fraction bar right here, this fraction bar for the whole thing, is division. And if we want to divide by h over 1, we can multiply by 1 over h. Got that? Take it back a second if you need to. We're dividing by h over 1, which is the same as multiplying by 1 over h. Okay, so what do we have? If we look at this fraction, we can, because this is multiplication here, we can cancel this at h. Let's see if I can change the color here. Well, too much trouble. Let's get this color. So we can cancel this h, get a 1, cancel this h, get a 1, and what do we have? On the top we'll have minus 2, on the bottom we'll have x times x plus h. And that will be our average rate of change. Now it doesn't say anything about instantaneous, so the h stays exactly where it is. This is our average rate of change, and h can be whatever you want it to be. We're not saying h approaches 0 this time. Got that? Moving on. There's their working of it. We're subtracting the x's to get the delta x. We've got our f of x's. We're going to subtract those. Put those values in, x of x plus h and x. Get a common denominator. A little bit of algebra. See that h over 1 dividing by that is multiplying by 1 over h. And then the h's cancel out, giving us 1's. And there is our answer. Okay, next. We're going to look at a particular example where we can use something a little bit closer to reality. We've been playing with algebra, so to speak, and we're going to look at an object falling from an airplane. Now, this is not suggesting to you you should drop things out of airplanes. There could be someone on the bottom, or you could hit an apple tree or something. That's not good. Now, what does this mean? If you look at this first column, and I'm going to put this back to red so you can see it again. There we go, back to red. Alright, so these are t values, which, if you're familiar with x's and y's, that would be like the x values. But these are in seconds, so this particular line represents what's happening at 0 seconds, in other words, when you start this experiment. And the second one says, how far has that object fallen from the airplane at this point in time? Well, it hasn't fallen at all, so it's 0 feet. Second one, after it's fallen for 1 second, how far has it gone? 16 feet. After 2 seconds, it's gone 64 feet. After 3 seconds, 144 feet, and you can see the last two. Now this last column is talking about what is the difference in the distance in subsequent values of d. So we're going from a 0 here to a 16 there. 16 minus 0, the difference in the distance in going from 0 second to 1 second, it's gone 16 seconds during that second interval. The next time, going from 1 second to 2 seconds, how far has it gone during that time interval? It's gone 48 feet. In going from 2 seconds to 3 seconds, it's gone 80 feet, which is the difference between these two. We're subtracting them all the way. 4 seconds, it's gone 256 feet. In the 4th second alone, it's gone 112 feet. In the next interval, it's at 400 feet below the airplane, and during that 5th second, it was going 144 feet. So that's what happens during the first 5 seconds of its descent. And incidentally, in case you're a real practical person, this is ignoring air drag. So there's no air out there, we're just making it real simple. So first of all, how far does the ball fall during the first 3 seconds? We'll sneak back here and look. 3 seconds, it's fallen 144 feet. 144 feet. Next, what's the average velocity during the first 3 seconds? Remember, delta D over delta T, or the second distance value minus the first one over the first time value, or the second time value minus that time value. How far is it gone? At second time, which is at the 3 seconds, it's gone from 0 seconds to 3 seconds. So on the bottom we could fill this in real easily. It's gone to 3 seconds from 0. That's the time interval for the first 3 seconds. Went from 0 seconds on your stopwatch to 3 seconds. On the top, where was it at 0? Let's sneak back here and look. At 0, it had gone 0 feet already. So this is 0. Where was it at 3 seconds? Sneak back here and look. At 3 seconds, it was 144. So go back here. There's our 144. So delta T over, D over T equals, we'll go 144 over 3, which is 48. And remember, this is velocity. And what we have on the top here is feet. So it'll be 48 feet per. And what did we have on the bottom? We had seconds. There's our second answer. How fast is the ball traveling when t equals 3? That's a different story. This first one is, what's the average speed from 0 seconds to 3 seconds? How fast is the ball traveling when t equals 3? Let's take a look. Here's part A, part B, part C. We don't know. You weren't expecting that, were you? We don't know. Okay, we're getting there. So the slope on the point of a curve for average speed, remember we have a time interval. So we're going from one point to another point in the average speed. For instantaneous, we go to 1 point, not 2 points. So instead of thinking of what was my speed as I went from Spartanburg to Raleigh, North Carolina, for example, instead of that, it's, okay, when I got right in the middle of Charlotte, how fast was I going then? That would be the instantaneous rate of change. And if I'm staying within the speed limit, maybe somewhere around 60 or 65, depending on the limit. Certainly not 80 or 90 or anything like that. Next, the difference quotient. That should look familiar. What might not look familiar is the fact that this is representative of a secant line. What's a secant? Well, let's take a generic curve. Say we've got a curve like this, and we're going from this point to this point. The secant line is the line that connects 2 points on that curve. 2 points that are not at the same place. That's a secant line. H is how far it is horizontally from where it began. Notice, very important, for x equals a is the height of the point. Remember, this is the y value. Don't lose track of that. The slope of the curve at the point is f prime of a, because f prime represents slope. The slope where? The slope where x equals a. So for x equals a, you get two things. What's the y value? Just put the a in where the x's are in the function. You want the slope, put the a in the rate of change, and you can find out what the slope is. Is it going fast? Is it going slow? Uphill? Downhill? You can tell all that. All right, we're talking about South Carolina. I think some of you know where South Carolina is. And we're interested in is f prime of 8 positive, negative, or 0? And what does it say? It says on a typical summer day, that makes some of us sweat already, where t is the number of hours since midnight. Oh, that's pretty simple. That's 0, 0 sort of, especially military time. T equals 1 corresponds to 1 a.m. T equals 13, 1 p.m. Now, what is that? I'm going to check, make sure. Yeah, I haven't missed anything. So we want to find out three things. And since the graph of f of t will increase, so remember, what we're doing is we're going from time 0, which is midnight. And what were we talking about? We're talking about the temperature. So we're going from midnight to 8 a.m. Remember, this isn't 8 p.m. That would be f prime of 20. So we're going from midnight to 8 a.m. What's happening to the temperature? In South Carolina, you've been here, from midnight to 8 a.m., what's happening? Well, actually, it's still cooling off because the sun hasn't come up yet, for the most part. So if it's cooling, that's sort of like a rate. What's happening to this? The slope is positive, and that means it's warming up. See? Why does it say mid-afternoon? Let me check back here a second. I think they made a mistake. You know what South Carolina is like. At 8 a.m. Oh, my mistake. At 8 a.m., what's happening to the temperature? Well, the temperature's gotten about as low as it's going to get. If you get up at 8 a.m. in the morning, what's it going to do from there on? It's going to get hotter. So, slope is positive. It's easier to work with the algebra sometimes. A lot of logic in this. Second, let's clear this. Here's our ink on the slide. There we go. At 9 p.m., the temperature's begun to decline, finally. With the sun down, it'll be getting cooler. That means the temperature's going down, so the slope itself will be negative. Should make sense. So this is a little bit of a picture, and I challenge you to hit the pause bar, take a look at various parts. This is midnight. This is the next midnight. Here's at 8 a.m. in the morning. Notice it's been cooling down, and then it started heating up and up and up. Somewhere around 4 o'clock perhaps, it's about as hot as it's going to get, and the sun starts going down, and the temperature starts dropping. All right, here's one about cost. We're making bookcases, metal bookcases. We've got some givens. So we're given that C of 300 equals 31,000. Okay, first of all, what does this mean? Notice that C represents the cost of making X bookcases. So this means that the cost of making 300 bookcases is $31,000. What does this mean? This means that when we're to the point where we've made 300 bookcases, how much is it going to cost to make the next bookcase? 90. Because at that point the slope is 90, notice it's positive, so the cost, the total cost, remember that's the total cost is going up by 90. Not for that one bookcase, but for the next bookcase. Sketch a tangent point to it at 300, 31,000. This is what we had at first. Estimate the cost of manufacturing 303 bookcases. Okay, let's go back up here. What we want is an estimate of what this is going to be. What's the cost to make 303 of them? Excuse me a sec. Okay, so what have we got? At 300 bookcases, I'm going to make this short. It costs us $31,000. And if you think about it, if you make 3 more, it's going to have to go up. So what is it going to be at 303 bookcases? Sneak back up here. What's happening to the cost once you get to that 300 level of manufacturing? Well, it says that at this point, where you're making 300 per day, for example, every extra one is going to cost you an extra $90. We're making 3 extra ones. Each extra one is going to cost $90. So for those bookcases, we've already figured we're going to spend $31,000, and for each additional one it's going to be $90, but we're doing 3 more of those. So the total cost, we're making 303 bookcases. This is our estimate on paper. We the 31,000 plus 270, or $31,270. There you go. All right. Here's our graph, our initial question, and that's how the cost is going up. And there's the explanation again of how you get to the 303. Let's go to the average cost, which is 103. X. Okay. So this is what the slope looks like. So we're interested in what's going on at this X value. Sometimes this will represent a time. Quite often it will represent a time. Now if we're talking about average of something, we might talk about what's happening from here to here. So we can just subtract the x's and get the denominator of the slope, subtract the y's, and get the numerator of the slope, and that will be the rate of change for that particular function. How about this one? We'll start with delta y over delta x to get our average rate of change. We're going from 0 to 3, so in the denominator we'll have 3 minus 0. In the numerator, if we put a 3 in where the x is, that's going to give us 3 cubed, that's 27, divided by 3. The function value will be 9 for an input of 3. If I put a 0 in for the x cubed is 0 times anything is 0. There's our average rate of change. Simplify that a small bit, and there's our slope from one to the other using the average rate of change. And the details, and there's the answer. So this is perhaps the point we're interested in. The secant line takes us to a second point. Remember, we're talking about average rate of change. So there is an actual delta x. We're not making it close to 0. There is an actual delta x because it's over a period of time. And this is what happens to y value, whatever it represents, when you go from an x of 0 here to an x of 3 there. Here we've got another graph. Try to look at the graph and think about what it actually represents. These y values over here represent the height of the arrow. And down here, 1 second later, 2 seconds later, 3 seconds later, 4 seconds later, and so on. As if when we let go of the arrow, someone hit a stopwatch, and this tells us how high the arrow is at each of those points. Here's our graph, or excuse me, our equation. Time is what's changing, and if we put in this function, f, that function tells us the distance in the air that arrow is. In fact, it tells us a little bit more if we pull this thing apart. The 80 means that the arrow, when you left it go, was going 80 feet per second in the air. Notice the positive 80, that means it's going upward, or the distance above the earth is getting bigger and bigger and bigger. However, on this side, the negative 16 actually says a little bit more than you expect, perhaps, because you could think of this as, if you're going back to physics, if any one of you have taken physics, this corresponds to 1/2 gt squared. Now, g has to do with gravity. That's why we use the g. And gravity has an acceleration of 32 feet per second squared. The reason it's negative is because the gravity pulls us downward, pulling the arrow in the opposite direction from what it started. This g is negative 32. When we take this half of it, we get the negative 16. That's where the negative 16 comes from. And this whole thing tells you how far in the air that arrow is at any particular time t. This is the initial speed getting us in the air, which is eventually overcome by the fact that gravity is going to pull it down. So, 4 questions. A, where is it at t equals 3? Our equation is f of t equals negative 16t squared plus 80t. All we need to do is put the 3 in there. So f of 3, the distance, the height of the arrow at 3 seconds is negative 16. Put the 3 in for t, which gets squared, plus 80. And again, t of 3 here. So we've got 9 times 16 is negative 144, plus 8 times 3 is 24. Okay, did I make a mistake here? I don't think so. B, what's the velocity of the arrow at t equals 3? What's the velocity? Okay, we can sneak back here. It doesn't tell us what the velocity is, but we can take this f of t, that's our distance function or height function, negative 16t squared plus 80t. Now what you can do is use t and t plus h to get the function for the velocity of the arrow. I'll let you do that, hit a pause, come on back. What you should get, this is average, the velocity of the arrow will be, let's see, velocity of the arrow. Okay, let's move ahead here. Let's see how they do it. Okay, there's the first one. Just put the t in. Oh. Well, that was pretty silly. I left out the 0. Did you catch that? 240. Now we can get the right number. 96. 96 feet high. Okay, instantaneous velocity. So we want the slope of the tangent line, and when we get that, we're going to evaluate it for what it is at t equals 3 seconds. Instantaneous, not average. So go to the difference quotient. There's our h in the first function and h on the bottom. Expand that, subtracting the original function out there. Here's the t plus h part of the original function. Here's the original function. Don't forget to square this before you multiply by the negative 16. Simplify it a little bit. So there it is expanded. Some of those parts will cancel. Like for example, you're going to get negative 16t squared there, and with that 16t squared here, that'll give you 0. Keep going, and then divide by h. Cancel those h's out. And there is your formula for instantaneous velocity. Now you find the limit. Now h is approaching 0, and this polynomial right here with a limit. Since this is a polynomial, you can just put the 0 in where the h is, and there's your velocity function. Now we wanted the velocity at t equals 3. How fast is it going at exactly the third second? It'll be the tangent on that graph. Just put the 3 in for t. Negative 16. Negative 16 what? Negative 16 feet per second is how fast it's going at t equals 3 seconds. That means it's headed toward the ground, and let's hope that you're not underneath the arrow. So we know that the slope is negative 16. We can interpret the derivative two different ways. The instantaneous rate of change, or the slope of a tangent line. Over here, here's x equals 3. So if we go up here, here's the point at t equals 3 seconds. Notice that it's changing speed. It's getting faster, but it's going faster in a negative direction. It's got a negative slope. These two work together. The first one is an algebraic look at things, and the second one is a geometric look. So if we set f of prime equals 0, when does it hit its peak? Well, at the peak, it's actually going to be going 0 speed at all. So we can set the velocity equal to 0 and solve for t. A little bit closer, divide by negative 32. You get a positive number. Cancel out the 16s. I'm not sure that you really need to do that, but 5 halves. After 5 halves of a second, or 2.5 seconds to most of us, that's when it stops going upward and starts going downward toward us or toward the ground. The peak is at 2.5 seconds. Estimate the slopes at those points. Notice in particular when it makes a 45-degree angle with the x-axis, it has a slope of 0. Oops. Erase that. Should have a quick eraser. There we go. Nice to have these on the same line. The slope of 1, 45 degrees. That's a good one to remember. Slope of 1, 45 degrees means if it goes 1 in the x direction, it goes 1 in the y direction. You make a small picture for yourself like this. Go 1 in that direction, 1 in this direction. The slope is a 45-degree angle. 45 degrees. When the slope is 0, that means perfectly flat, and the slope is 0. Just like as if you were walking along or riding your bicycle along, there's no slope at all. Or, excuse me, 0 slope. No slope is a different story entirely. So, here's a picture. Notice what's going on at each of these points. Notice that point A, down here. Always think of going left to right. So at A, we're going upward, a bit on the steep side. Notice it's more than 45 degrees if you draw a tangent here. Steeper than 45 degrees. Slope is positive because it's going upward. It's more than 45 degrees, so the slope is greater than 1. Up at B, that looks about like 45 degrees. Slope is 1. Up here at C, it's leveled out, so slope is 0. Over here at D, we're going downhill, so the slope is negative. And it looks as though it's about, it's hard to tell exactly. It looks close to 45, but according to this, it's a little bit bigger than -1. So I guess it would be nice to have some actual numbers to figure that out. At E, it's bottomed out, so it's horizontal, slope is 0. Over here at F, it's still going upward, so the slope is positive, but it's not going up 45 degrees. It's a little less steep than 45 degrees. Let's say 30, just for the fun of it. Last of all, at G, it's turned around up here. We didn't mention this point up here, where the slope is 0. Down here at G, it's going down very steeply. Negative because it's going down, and because it's more than 45 degrees down, the slope would be less than -1. So a couple of notes. This represents slope of a curve. This is the actual point that we're talking about. Now, at this point, we've got this slope and this steepness. This is the instantaneous rate of change. Again, it's at this point. Put this number in for x. This calculates the y by using the function f. The number f prime of a is called the derivative. So here we are. We're talking about derivatives finally. It's the derivative of f of x at x equals a. At different x values, you'll have a different derivative. Might have a different sign. It might be the same. The derivative of f of x at a particular point. So how about f of x at those points marked on the graph? I think we already, well actually we've got a different graph coming up here. Here's a new graph. It's not the same as the last one. So A, it's going uphill, so the slope is positive at A. At B, it's horizontal, so the slope is 0. At C, it's going downward, so the slope is negative. At D, it's still going downward, the slope is negative. E, it's leveled off, it's horizontal, the slope is 0. Possible graph of f prime of x. And this can be really tricky. We're going to sort of slide through this one. And that's it for this particular one. I hope you stuck with it through there, and for occasional mistake on my part. Alright, see you next time when we'll attack 2.3, and take care. Bye-bye.